Welcome to the next installment in the video lectures for managerial economics. Here we are going to be looking at Chapter 5, in particular the Q&As that appear in your textbook. So we're going to look here at Q&A 5.1. For a linear production function, Q is equal to 2L plus K, and a multiplicative production function, Q is equal to LK. What are the short-run production functions given that capital is fixed at K equals 100? Also, what are the marginal products of labor for these short-run production functions? So here we have the important pieces of information. We have that capital is fixed and is equal to 100. Here on the linear side, we have our linear production function. And here on the multiplicative side, we have our production function that's multiplicative. So all we need to do is we need to insert 100 for K in each of these production functions. So in the short run, our linear production function is Q is equal to 2L plus 100. And for the multiplicative production function, in the short run, the production function is Q is equal to 100L. In order to get the marginal product of labor, all we need to do is take the first derivative of the production function. That is, we're going to take a look at the change in Q whenever we change L. So for the linear production function, the change in 100 is going to be equal to 0. And if we take the derivative of this, we see that we are going to end up at the marginal product of labor is going to be equal to 2. If we do the same thing for the multiplicative, if we take the derivative of this, we end up at the marginal product of labor is equal to 100. Q&A 5.2, a manufacturer produces a container of potato salad using 1 pound of Idaho potatoes, 1 pound of Maine potatoes, or 1 pound of a mixture of these two types of potatoes. Does the marginal rate of technical substitution vary along the isoquant? And what is the marginal rate of technical substitution at each point along the isoquant? And as you noticed here, we've underlined or highlighted, or I would say underlined or highlighted, but we've put a shadow on this important piece of text here, because what this is telling us, it's giving us a very important piece of information, telling us that we can use a pound of Idaho potatoes, or we can use a pound of Maine potatoes, or we can use a pound of a mixture of these two types of potatoes. What this is telling us is that these inputs, Idaho potatoes and Maine potatoes, are perfect substitutes for one another. We can use a pound of one, a pound of the other, or we can mix them together and we get the same type of product. So they are perfect substitutes for one another. And that's what isoquants look like when they are perfect substitutes for one another. So we have Q1 isoquant here, the Q2 isoquant here, the Q3 isoquant here, and the Q4 isoquant there. So given that these are perfect substitutes, we have a straight line for the isoquant. So the first part of the question was, does the marginal rate of technical substitution vary along these isoquants? It does not. These are straight lines. The slope is constant on these isoquants. The slope does not change. The marginal rate of substitution, of technical substitution, does not change. So make sure you remember that if you have inputs that are perfect substitutes for one another, that the marginal rate of technical substitution does not vary along those isoquants, because when they are perfect substitutes for one another, we have an isoquant that is a straight line. In a straight line, the slope does not vary. What is the actual slope of these isoquants? It is equal to -1. If we take a look at Q1, we could be at this point here where we're using nothing but Idaho potatoes, or we could be at this point here where we're using nothing but Maine potatoes. If we're at this point here, in order to move to this point, we have to lose a pound of Idaho potatoes in order to gain a pound. So we have -1 divided by 1, which gives us -1. The same thing for Q2. If we move from this point here to this point there, we lose 2 pounds of Idaho potatoes, and we are using, instead of using 2 pounds of Idaho potatoes, we are using 2 pounds of Maine potatoes. So it is -2 over 2, which is equal to -1. So in this instance here, where there's perfect substitutability between them, we have a slope of the isoquant is equal to -1, and that is the marginal rate of technical substitution is -1 for these isoquants. For Q&A 5.3, under what conditions does a Cobb-Douglas production function given by Q is equal to A times L to the alpha times K to the beta exhibit decreasing, constant, or increasing returns to scale? So we want to take a look at a Cobb-Douglas function, and we should be able to tell by looking at it whether or not it is decreasing, constant, or increasing returns to scale. So there is our Cobb-Douglas production function, and we're denoting the output for this production function as Q1 because this is going to be our first output level. And what we want to do is we want to double the amount of inputs we are using. That is, we're going to double the amount of labor and we're going to double the amount of capital. So that'll be our new output level. So Q2 is going to be equal to A times 2L to the alpha multiplied by 2K to the beta. So all we're doing here is we're doubling the amount of labor and doubling the amount of capital. Using some mathematics, we can factor out the 2 to the front. So we have 2 to the alpha times 2 to the beta times AL to the alpha times K to the beta. And we can simplify that even further, that we will get 2 to the alpha plus beta power multiplied by AL to the alpha and K to the beta. Well, when we take a look at this, if you look at this right here, we already have this information, right? We already know that Q1 is equal to AL to the alpha K to the beta. So we could substitute Q1 into here. So we get 2Q is equal to 2 to the alpha plus beta multiplied by Q1. And to simplify that a little bit further, we will just assume that gamma is equal to alpha plus beta. So we have Q2 is equal to 2 to the gamma multiplied by Q1. All right, so we're going to take a look at this and see under what conditions are we going to get constant, increasing, and decreasing returns to scale. So we're going to keep those pieces of information, and let's assume that gamma is equal to 1. That is, alpha plus beta is equal to 1. Under that scenario, that if gamma is equal to 1, then we have Q2 equals 2 to the first power multiplied by Q1. That is, Q equals 2 times Q1. That means by doubling our inputs, our output will exactly double. Therefore, we have constant returns to scale. A doubling of inputs leads to a doubling of outputs. If we assume that alpha plus beta is greater than 1, that is, gamma is greater than 1, so we have Q2 equals 2 to the gamma multiplied by Q1. That means that part there, 2 to the gamma power multiplied by Q1, will be greater than 2 times Q1. So we will have, for example, 2 to the 1.2 power. That is going to be greater than 2 multiplied by Q1. So we have, or we can, let's even make it simpler, we could have 2 to the second power. So we will end up with 4Q1, which is greater than 2Q1. That means we have increasing returns to scale. We doubled our inputs, we doubled both capital and labor, and we more than doubled our output. And finally, if gamma is less than 1, if alpha plus beta is less than 1, then Q2 is equal to 2 to the gamma power multiplied by Q1. So that would be equal to, for example, gamma was equal to 0.5. So 2 to the 0.5 power multiplied by Q1 is going to be less than 2 to the Q power. Therefore, we're going to have decreasing returns to scale. So remember that with a Cobb-Douglas production function, the exponents on labor and capital, if the exponents on labor and capital equal 1, you have constant returns to scale. If you add the two exponents together on labor and capital, and it is greater than 1, you have increasing returns to scale. And if you add the exponents on labor and capital, and it is less than 1, we will have decreasing returns to scale.